emanating from this orifice of this fluid. And we're going to use Bernoulli's equation to do that. All right, so let's just go ahead and state how some of these things are going to behave. Let's say that this fluid at the top here is, or V1 is going to be equal to 0. In other words, it's not going to move, all right? We want to maintain its level. So in maintaining its level, that means that this piece, and let me choose a different color, a different method. This piece is going to end up being 0 because velocity is 0, all right? The atmospheric pressure, we'll deal with that in a second, and Y1 is just going to be equal to YF. So we need to keep all of that right now. Also, if Y2 is equal to Y initial, then we know that Y initial is just 0 because it's our origin point. Then this piece is going to go to 0. So we have a simplified equation. We're eliminating a couple of things. And let's just keep going. Let's keep right on. And let's rewrite the equation above. P1 plus rho, which is the density of the fluid. It's just the density of water. I hadn't mentioned what density is, but it's just the density of water. And then we're going to have G times Y sub 1. So we know that that's there. Equals to P2 plus 1/2 rho times V sub 2. So again, we're looking for V sub 2. So let's just go ahead and write this on another page. So remember, we have P1 plus 1/2 rho. Nope, we don't have that. We have rho G Y1. Let me see, make sure. Yep. Times equals to P2 plus 1/2 rho V sub 2 squared. All right. Now let's just take the P's to the same side. P1 minus P2 plus rho G Y1 equals to 1/2 rho V sub 2 squared. What we have here is a scenario where we know that P1 is just equal to P2. Therefore, we can write 1/2 V2 squared equals to rho G Y1. So all that means is that this piece right here is just 0. Because the atmospheric pressure on the top that's pushing the water down, okay, it's not only the atmospheric pressure, but it is atmospheric pressure. And the atmospheric pressure on where the orifice is coming out, they're the same. Now, if you have more pressure at the top, you'd have a pressure differential. So you know if you have a pressure differential, you're going to cause something to happen. You're going to cause that water to push, all right, to come on out. So if I put a weight on top, then it'll come out even faster. All right, enough of that. So let's go ahead and solve for V sub 2. We see that we have rho's on both sides, so we can eliminate those. So V sub 2 squared equals to 2GY1, which implies that V sub 2 is just equal to the square root of 2GY1. This is a familiar equation. We did this with the conservation of energy, all right? In fact, well, we did this with the conservation of energy. We came out with the same solution, okay? So we're gonna be using this in Bernoulli's equations, all right? And so Bernoulli's equation is ideal. When I say it's ideal, that means it's non-viscous.